Hello, my name is Ruta Vaitkeviciene and I'm from Lithuania. Today I will present to you the ultrasound-assisted production and characterization of resistant starch from rice milling byproduct them. So let's start. And first of all, about me. I am the last year PhD student of Department of Food Science and Technology from Kaunas University of Technology. A topic of my dissertation is valorizations of rice processing secondary food raw materials into functional food components by ultrasonic treatment and microbial fermentation. My research is focused on brown rice polishing waste for the fermentation, lactic acid bacteria, and ultrasound treatment for productions of resistant starch. So, my research, brown rice polishing waste, I used rice bran, microorganism, and lactic acid bacteria, Pediococcus, Lactobacillus, and others. Antifungal activity against pathogenic microorganisms and Fusarium, Fusarium graminearum, Fusarium culmoro, and other fungals. Ultrasound treatment procedures, and the new project, resistant starch from rice bran. Rice bran, the material of this study, is rice processing byproducts enable the industrialized production of functional ingredient for foods. Rice bran were fractionated into fractions according to particle size using a laboratory sieve shaker. Rice grain, rice with bran, and after shaker, we have rice bran and rice. So in table 1, you can see rice bran fractions, 1 to 3 fractions, and in the study was using rice bran fractions 315 micrometer size. In table 2, you can see main chemical components of rice byproduct: moisture, protein, fat, starch, dietary fiber, and ash. Resistant starch. In this presentation, a dual ultrasonication retrogradation treatment was provided for the production of resistant starch in rice bran, and it is effect of resistant starch structure and functional properties was evaluated. Resistant starch is a part of starch which are not accessible to digestive enzymes and has some of the same physiological effects as dietary fiber. Methods: ultrasound treatment of rice byproduct, resistant starch content determination, scanning electron microscopy, hydration properties, water and oil absorption, viscosity analysis were measured using an Ostwald capillary viscosimeter. Ultrasound treatment. Rice bran was weighed and mixed with the distillate water, and the samples were sonicated with a low frequency ultrasound using ultrasonic cleaning at temperature from 30 to 70 degrees and different time periods: 15, 20, 25, 30, and 35 minutes at 100 and 120% intensities. Measurement of resistant starch was performed according to using the resistant starch as a kit rapid megazyme test, following the procedures provided by the manufacturer with a slight modification. This method using 2 enzymes, the pancreatide alpha aminolase and aminoglucosidase. Samples are incubated in a shaken water bath in linear motions with saturating levels of purified PAA and EMG for 4 hours at 37 degrees temperature. During this time, non-resistant starch is solubilized and hydrolyzed to D-glucose by the combined actions of the two enzymes. So you can see measurement of resistant starch. Sample, 2 methods, AOAR official method and rapid resistant starch method. In this study, I use rapid resistant starch method, PAA plus IMG 4 hours, 37 degrees, pH 6. After 4 hours, addition of ethanol, stop reaction, and recover resistant starch pellet by centrifugation. After washing off resistant starch pellet, 50% ethanol twice time, and all supernatants measure digestible starch in supernatants. Bad pellets, dissolution, and hydrolysis of resistant starch need neutralized with acetate buffer, incubated with IMG, and measurement of glucose with Gopot reagent. Calculation of resistant starch. Results of resistant starch. The kinetic of ultrasound-assisted productions of resistant starch was performed using continuous and pulse ultrasound, respectively at different time and different temperature. The results of resistant starch production rate are shown in figure 1, and the resistant starch content measurement of different ultrasound processing time points was compared to the initial content in untreated material. In this point, 11.38 gram. The resistant starch content in the case of continuous ultrasound, a significant increase in a range of 11.41% in the content of resistant starch and temperature between 30 and 50 degrees temperature was fixed depending on processing time. The highest increase in resistant starch content was observed at 15-20 minutes of sonication before decreasing at 25-35 minutes. However, ultrasound temperature of 70 degrees caused a significant decrease by an average about 76%. And the resistant starch content not dependent on time, while sonications for 15 minutes at 60 degrees emission by increased by about 25% in resistant starch formation. So the next method, scanning electron microscopy. The scanning electron microscopy of resistant starch granules from untreated and ultrasonicated at a different temperature for different times rise byproduct are presented in figure 2. Some micrograph of untreated rice resistant starch showed typical small spheroid granules, irregular in shape and agglomerated, and a smaller part of large disc-like particles. The changes in resistant starch granule morphologically become more visible when the ultrasonic exposure time and temperature increase. The ultrasonication for 20 minutes at 40 degrees temperature already indicated the disintegrations of large granules, while ultrasound even for 30 minutes resulted in an aggregations of small irregular shape granules and the formations of a film-like structure. So in our study, the increase in sonication temperature from 40 to 50 degrees temperature, tending to more intensive fragmentations of large starch granules, aggregations of small granules, and the gelatinizations of resistant starch matrix in the case of 70 degrees temperature. Overall, in resistant starch from ultrasound-treated rice bran samples, only visible fragmentation change was seen. The results of amylose and viscosity. Appearance, amylose contents, and crystallinity of a resistant starch granule was analyzed at ultrasound time points, and the values of amylose for ultrasound-treated samples were significantly higher than untreated resistant starch, increases with the increase in ultrasound time and temperature. The highest amylose content was observed at 40 degrees temperature for 30 minutes, sonicated resistant starch with the corresponding values of about 55%. The lowest apparent amylose content was determined in 70 degrees ultrasound-treated resistant starch samples, about 45%. So following retrogradation, the linear amylose change having higher flexibility recrystallized and from tight to packed to double helicized, stabilized by hydrogen bonds that are resistant starch to enzymatic hydrolysis. Results of water and oil absorption capacities and viscosity. The highest water absorption capacities and oil absorption capacities were found at 70 degrees temperature, sonicated resistant starch samples, which were significantly higher than that in the control values. When ultrasound was performed longer or under higher ultrasound temperature, the starch granules were heated and the inertial matrices of the starch granules changed from an order stage to disintegrated conditions owing to the absorptions of water by amylopectin of resistant starch, which led to increased swelling. And in conclusion, the main effects of ultrasonic treatment were degradation of starch granules and depressions on rare surface, especially due to ultrasound temperature increase. Ultrasonic treatment increased amylose content and disagreed viscosity of resistant starch. FT analysis indicated that ultrasound treatment disagreed the crystallinity of resistance starch and increased its amorphous character, causing an increase of fat and water absorption, solubility, and swelling power. The development technology brings low temperature ultrasound processing of the rice milling byproduct to develop a new functional food ingredient. So that's all. Thank you for attention.